So we are moving on to everyone's probably least favorite topic, which is limits. And then that also leads into that concept of continuity. Because remember, continuity is always defined in terms of a limit. What I'm going to do now is I'm going to give you a formal definition of what a limit looks like in multivariable. However, in practice, this is extremely difficult to actually do. And unless you're going on to advanced calculus, you're not going to ever go through this approach. But it's something that everyone needs to see if they're in a STEM career or a calculus-based career. So I don't want you going on to higher level classes without seeing this formal definition. In practice, though, actually evaluating limits for multivariable functions is super difficult. It's hard to show a limit exists. It's much easier to show a limit does not exist. Okay? So we're going to start with the formal definition for a multivariable limit. So we're going to let the point AB be an interior point in the domain of a function f of xy. This concept does extend to functions of more variables, has a very analogous approach. It just depends on what the distance looks like in whatever that space is. But we're just going to work with two input variables. So here we say that the limit of this function, f of xy, as xy approaches AB, is equal to some number L if and only if for all real numbers which we call epsilon being positive, there exists a real number delta, which is positive, such that the following is true. Okay? So epsilon and delta, they're just Greek letters. Okay? Basically, if you remember from Calc 1 or even pre-calculus, when we talked about limits, we kind of had like a wishy-washy definition of saying, oh, I can make the output arbitrarily close to this value L as long as my x was close enough to this value A that you were approaching. This is really just the formal definition of that. So I want to know that this limit actually equals L if the following holds. You can make the output values as close to L as you want. That is all this expression is saying. If I take the difference between the output of our function and this limit L, it is as small as I want to make it. Okay, so I can make the output arbitrarily close to L. Whenever my point is close enough to AB. So the way we say that is I can make the difference between my function and L less than epsilon, so as small as I want, whenever my value xy is close to AB. So I'm going to actually write this a little bit different way. So that would be the distance between those 2 points. So for us, that distance is a square root. Whenever I make x and A and y and B close together. So again, I can make my output arbitrarily close to the limit L whenever my input is close enough to the thing I'm taking the limit of. So xy is approaching AB. I'm making that difference or that distance between those as small as I want. Okay? So this is just the more formal definition, which you can see why we might not show you this in pre-calc especially. But even Calc 1, this is pretty intimidating. There's actually an even better way to write this. So the formal way we talk about taking a limit is we say for all epsilon greater than 0. So this upside down A means for all. Okay. Remember, this is how close I'm making the output to L. So no matter how close I want these two to be, there exists a delta greater than 0. So this is another math symbol you might not have seen. This means there exists. Such that the difference between F and L is epsilon close whenever X and Y are delta close to AB. But not exactly equal to AB. Okay? So you might still be like, what the heck does this even mean? And that's okay. I'm going to show you a visual that I think will be a little bit easier. But again, it's giving preciseness to that wishy-washy definition we had before. So thinking about this in terms of our function, here is our xy plane. And maybe our domain, I always end up choosing the same kind of lima bean shape, looks like this. Okay. So I have some point A, B. Okay. And I'm approaching that point. Then I've got this limiting value L over here. So L is that z value, the output of the function. Okay. What this definition is saying, if I take a small, we call it a perturbation, of a distance epsilon, and it's arbitrary. Okay. This value up here would be L plus epsilon. This value here is L minus epsilon. So say my limiting value is 7. This epsilon could be 0.00001. So if I'm looking between these two values of my limit, I can always find, basically it's called a delta ball around that initial point. So that no matter the value I pick inside this ball, it's going to give me within epsilon distance of that limiting value. Okay. So this is my delta radius. Okay. No matter the xy value I pick inside this ball, when I find the output of it, it's going to be within this range. Okay. So this is what my limit means. No matter how close to my limiting value I get, I can always find some value around what I'm approaching so that every single point inside of here will get me within that epsilon distance I want. Okay. So if you're going on and becoming a math major, you will go into advanced calculus and you will talk more in depth about this, but this is the true definition of what a limit means. No matter how close to L I want to get, I can find a region around that point I'm taking the limit of to get me within that distance. Okay. So now I'll write it in the terminology you're probably used to. In other words, if the values of f of x and y can be made arbitrary close to L, by taking points which are x and y values sufficiently close to AB, but not equal to AB, we write that the limit as the point xy approaches AB of our function is exactly equal to L. Okay. So remember again, for a limit, we really don't care about if the function is defined at that point. It's just what's happening as I approach it, right? So with these multivariable functions, a lot of the same stuff is still going to hold. You still have a lot of the same exact limit laws. So I don't really tend to go over those because you're used to them at this point. If you can directly plug in the point, excellent, go ahead and do that. But if you can't, our approach is going to be a lot different. It's much harder for multivariable functions, okay? Because if you think about back in Calc 1, we talked about one-sided limits. If you came in from the left versus coming in from the right, they had to be going to the exact same thing for the overall limit to exist. And if they didn't, you were good, it didn't exist. With this, we don't really have a set way to approach a point in 2 dimensions. You actually have a ton, okay? So with this definition, we don't care about the direction. No matter the direction you approach from, it should go to the same thing. So proving existence is a lot harder because back in Calc 1, you just had to check from the left and right that they were doing the same thing. Here, you have way too many directions to actually test that it's impossible to go through that approach. So let me kind of summarize all of this in 2 words. So it's much more complicated to compute limits for multivariable functions. Okay. So for functions of one variable, there were only 2 ways to approach a point. From the left or from the right. Okay. So in Calc 1, you had your x values, you let x approach a. You could only come into that value from 2 directions. For us, we now have a point we're approaching. So here's our A, here's our B. The limit does not indicate the direction. So I could come in this way. I could instead come in on a diagonal path up to that point. I could come straight down like this. I could come at an angle. There are an infinite number of ways I can approach that point. I can make it messy and come in on a trig function. I can make it come in through a natural log. There's no set way to approach a point. Okay? So however, for us, the definition for a limit of a function of two variables has no direction involved. Okay. This doesn't help us for showing a limit exists. However, it does help us for showing a limit does not. So back in Calc 1, if you showed that the limit from the left was different from the limit of the right, that was typical of your piecewise functions, then overall the limit did not exist. Well, the same idea is going to hold here. If I come in from one direction and then a different one, if they're doing different things, the limit does not exist either. So if I can find two paths that give me a differing limit, I'm golden. The limit does not exist. Okay? So that's at least one bright side. And again, it is much easier to show a limit does not exist than it does. So here, if we can find two different paths, of approach that result in different limits, for the function f of xy. Then this limit as xy approaches ab for our function does not exist. Okay. So this is a process called the two-path test. If you find two paths that give you differing values, limit does not exist. So this states if f of xy approaches some value L1 as xy approaches AB along a path C1, and if this function approaches a different value as you let x and y approach AB along a different path, C2, where these limiting values are not the same, then you can say overall that this limit does not exist. Okay. So two paths to approach that point, going to different things, the limit does not exist. Exactly the same as saying the left and right limit are not the same, so the overall limit does not exist. Okay. This is going to be your first approach every single time. You're going to try a bunch of paths and you're going to see, do I get the same thing? Or do two of these give me something different? And if they give you something different, you are done. Okay. We'll see what happens in the case that you try the same path or try different paths and you get the same result over and over. Probably an indication that the limit exists and you might have to do something a little bit harder. So again, we like when the limit does not exist. Okay. Let's try an example. Let's go ahead and show that the limit as xy approaches 0, 0 of x to the fourth minus 4y squared divided by x squared plus 2y squared does not exist. Okay. So this one, at least nice, it's telling us the limit does not exist. So that means I need to find two paths that result in different things. So we need to find two paths which give us differing limits. Okay. So the point that I'm approaching is 0, 0. But you're going to see that's going to be pretty typical because when it gets to the other values, it's a little bit harder too. So we try to keep it nice. So this is the point that I'm approaching. Right? You want to try to pick the nicest paths to start with. And basically you're going to try those and see, okay, do I get something different before I have to get more complicated of a path? And then if I do get more complicated of a path and it's still giving me the same thing, that's usually an indication the limit does exist. So here, I'm going to start my first path really nicely. I'm going to go along the x-axis. So one way to approach 0, 0 is along the x-axis. And the reason this path is super nice is because y is equal to 0. Okay? Which is great. The next path that's going to be typical to try is then along the y-axis. And maybe it'll be that it results in the same thing. So then you can kind of start to get funky. You can think of the line y equals x. That approaches 0, 0. So you can approach it along this path. You could also approach along y equals x squared because that goes through 0, 0. The reason we're doing this is because by picking this particular path, you're going to turn it into a single variable limit, which you can actually compute. Right. Oh, didn't do that. Wanted to delete that. Okay, so let's start with going along the x-axis. When you're writing these up, you always want to be clear as to what your path is. So we're trying to evaluate the limit as xy approaches 0, 0 of x to the fourth minus 4y squared over x squared plus 2y squared. And again, because I'm picking this particular path, you're substituting in y equals 0. So this is the same as just letting x approach 0. And then anywhere I see a y, it gets replaced by 0 because we are on the x-axis. Why is it not writing now? Let's move that up a little bit. There we go. And then y gets replaced by 0. Okay. So you can see this makes things very, very nice for us. This becomes just x to the fourth over x squared. And that simplifies very nicely as the limit as x approaches 0 of x squared. And now I have absolutely no issues plugging this in. This limit gives me 0. Okay. Now I'm hoping if I pick a different path, I get something other than 0, 0. So let's try along the y-axis. Okay. I'll draw a little picture over here so we can see what's going on. The point I'm approaching is 0, 0. And if I'm coming along the y-axis, then my x is going to equal 0. Okay. So this limit along this particular path will turn into the limit now as y approaches 0. Okay, because my x I'm setting equal to 0. And this will give me 0 to the 4th minus 4y squared over 0 squared plus 2y squared. And then simplifying this, that gives me negative 4y squared over 2y squared. And then some nice stuff happens. You've got y squared over y squared. That just cancels out. And this gives me the limit as y approaches 0 of negative 4 over 2 is negative 2. So this limit is overall negative 2. So what ended up happening is along one path I got 0, along the other path I got negative 2. If you've had me for calculus, you know I'm a stickler of showing or saying the result you're using to get that conclusion. So here what I need to say is since these two values are not equal, 0 is not the same as negative 2, by the two-path test. This limit does not exist. So it's a named statement that I'm using. I've got to actually state that in my conclusion to say I get this result. Because I got two different limits along two different paths that both approach 0, 0. The limit does not exist. Okay. Now the biggest misconception that happens is the exact opposite of this. You get in a habit of, okay, well, I'm trying two paths. If you get two paths are the same, then great, your limit exists. But that's not true. So the two-path test only tells you about a limit not existing. It tells you nothing about a limit actually existing. So you cannot use the two-path test to actually state the limit exists. Okay? You have to do something different in that case. So this is a big caution. This happens every single time. You should never use a two-path test to show existence. It's just like in Calc 2 when you use test for divergence to say that a test is convergent. Not true. Okay? So it's very easy to misinterpret the two-path test. It tells us nothing emphasis on nothing about a limit existing. If this function approaches some value L along two different paths, C1 and C2, you cannot say that the limit of the function is then equal to L. This has to hold for every single path you try. And there is physically no way you can test every single path through that point. There are an infinite number of them. So this needs to hold for every path. Through AB. And you cannot reasonably test every path. Because again, you can make some very complicated functions that go through that point. You can have square roots, you can have fourth roots, fifth roots, you can have combinations of things. You can have trig functions that go through that point. You can have natural logs, you can have exponentials. It is physically impossible for you to test every single path through that point. So if you're using the two-path test to get existence of a limit, you're wrong with that, and you cannot get that conclusion. So just be very, very careful. It's a natural thing to want to do. Because realistically, what's happening with these is, again, you're going to test a bunch of different paths, especially if you have no idea if the limit exists or not. So you try a bunch of paths and see, okay, do they give me the same thing? Well, if they do, great. It's probable then that the limit exists. But you, again, still can't state that conclusion. It takes a lot more to prove the limit exists. And so we'll get to examples like that, but I still want to focus more on this two-path test so we can see the limit not existing. So I'm going to try another example now. And again, we're told the limit does not exist. So we're going to show the limit as xy approaches 0, 0 of 3xy over 2x squared plus y squared does not exist. So again, I'm going to pick my paths. I'm approaching 0, 0. So let's start with along the x-axis. And in that case, y is equal to 0. So you don't have to rewrite this every single time, because you can see it's tedious. So I'm going to just jump right into this. Turns into a single variable limit. X is approaching 0. So we've got 3x times y over 2x squared plus y squared. Well, all that does is it makes my numerator 0, the denominator 2x squared, which is just the limit of 0, so this thing is equal to 0. Okay? So along this path, my limit is 0. Let's try another natural path now. Let's go along the y-axis. So that's where x is equal to 0. And so again, all that's going to do now is it's going to change these x's into zeros. So this becomes the limit as y approaches 0 of 3 times 0y over 2 times 0 squared plus y squared. And really, the same thing happens. So you get 0 over y squared. So this limit is 0. Okay. So these two paths give the same value. So I've got to try something else. Okay. So in this case, I still need to go through 0, 0. This is the point I'm approaching. So one that might be good is the line y equals x. That goes through 0, 0. Okay. So our next path is along y equals x. So I'm going to write the full limit out now. So we've got 3xy over 2x squared plus y squared. Okay. If I'm going along this path, you can do one of two things. You can replace the x's by y, and you get a limit of y as y goes to 0. Or instead, you can also replace y by x and do the same thing. So I'm going to go with that approach. This is the same thing as letting x approach 0 and all of my y's turn to x's. Okay. And now here we can go through and evaluate this limit. We end up with 3x squared in the numerator. 2x squared plus another x squared is 3x squared. And then you can see nice stuff starts to happen because the x squareds cancel. And 3 over 3 will end up giving us 1. So this limit is equal to 1. Okay. So I have found two paths that give me differing values. So I can say is since 0 is not the same as 1, the limit does not exist by the two-path test. So we have just some common paths. You can see going along x equals 0, y equals 0. If you're approaching like 1, 1, then you would pick x equals 1, y equals 1. Some lines through it. But typically, again, we're going to be letting x and y approach 0, 0. Because realistically, you can shift things around to make it that limit. So those are going to be your most common paths that are easiest to work with. So the most common paths to choose are x equaling 0, y equaling 0, y equals x. You can pick a different slope, whatever you want. You can pick y equals x squared, or just similar functions that are easy to work with. And they go through 0, 0. So now we've hit that point. What happens if a limit exists? How do we show that? So we've got a couple things. To show a limit exists, we can use a definition, which I know you're not going to do or want to do, but you can. Okay. We can use algebra to manipulate. Or one of our other major techniques is we can use the squeeze theorem. So I'm going to do one more example, well, two more examples, but basically one of each of these. I'll give you an example where we use algebra to manipulate it, and then another example of using the squeeze theorem. So this one's going to be a little bit more complicated because they don't tell you what actually happens. We want to evaluate the limits if they exist. So you don't know, like in the other instances, what the end result should be. You have to figure it out. So let's start with probably the nicer of the two. Let's take the limit as xy approaches 0, 0 of x squared plus y squared divided by the square root of x squared plus y squared plus 1 minus 1. So you could sit here, if you plug in 0, 0, this gives you root 1 minus 1. The bottom ends up being 0, and then the top you have 0. So it's still technically one of those indeterminate forms. Okay. So right off the get-go, I'm trying to plug it in, but I can't. You get form 0 over root 1 minus 1. It's got 0 over 0. Okay. I can try some paths and see what does it give me. So I can plug in x equals 0. I can plug in y equals 0. But realistically, if I start by plugging in x equals 0, you'd have that radical in the bottom. And remember, if you had radicals, especially with the sum of two things, your main tool was multiplying by the conjugate to simplify it. And if I consider the other case, if I let y equal 0, same thing, I'm stuck with a square root in the bottom, minus 1. I would have to actually go through the conjugate or L'Hopital's, but that would be messy, to evaluate this. So there's nothing stopping me here. I've got a square root minus 1. Let's go ahead and multiply by the conjugate. So if I do that, that's the square root of x squared plus y squared plus 1 plus 1. And if I do that in the bottom, I've got to do it in the top. Okay. I absolutely do not want to distribute this stuff out in the numerator, so I'm just going to leave it as is, as something times something. So I got a giant fraction. I've got x squared plus y squared in the top times this radical. And then if I go ahead and FOIL the bottom out, when you have the radical times the radical, it cancels. And that leaves you with just x squared plus y squared plus 1. The outer term would be positive 1 times the square root. The inner term is negative 1 times that square root. So really, it ends up canceling out, which it should because it's the conjugate. And then when you do the last terms, it is just minus 1 times 1. So you get minus 1. Okay. So nice stuff happens. The 1 disappears. So in the top, I'm left with x squared plus y squared times this giant square root. And in the bottom, we are just left with x squared plus y squared, which is fantastic because now my problematic thing ends up canceling, which is also why I didn't want to distribute stuff out. So this disappears, and what we're left with is the limit as x and y both approach 0 of the square root of x squared plus y squared plus 1 plus 1. Okay. And now here you have 0 issues. You've got nothing in the denominator. You can directly plug in 0 for x, 0 for y, and simplify it from here. So we've canceled out the issue. So this becomes the square root of 0 squared plus 0 squared plus 1 plus 1. Well, that's root 1 plus 1, so this limit is equal to 2. Okay. And so this limit exists. It's exactly equal to 2. Because again, this didn't matter about the path. I didn't consider that at all. I just used algebra to manipulate it. So hopefully this one's not too bad. If you see radicals within there, especially the sum of radicals or subtraction, try just going through that conjugate approach. Let's try one more, and this is the not as nice one. So it is going to end up being our squeeze theorem problem. But again, you might not recognize it is a squeeze theorem at first. So here, if I'm trying to go about this, I might, again, not recognize what to do from the get-go. So it's going to be natural for me to try the two-path test. Okay. So I'm going to pick a bunch of paths and see what does it give me. If I end up trying like 3 paths or so and I'm getting the same thing over and over, that's the indication my limit does exist. But I don't know that yet. So let's try our first path along x equals 0. This turns into the limit as y approaches 0 of 0 squared times sine squared of y over 0 squared plus 2y squared. Well, that just gives me 0 in the numerator, so this is 0 over y squared, 2y squared. So this limit is equal to 0. If I try along y equals 0, so switching it up a little bit, this becomes the limit as x approaches 0, and then anywhere I see a y, it's going to get replaced by 0. And sine of 0 is 0, so this becomes 0 over x squared, and same thing, I end up with 0. So same result. Let's try one more nice path. Let's go along y equals x. So anywhere I see a y, I'm going to replace it by an x. And then we'll let x go to 0. So these two just become x's. So that's x squared sine squared of x over x squared plus 2x squared. Well, I can add together that numerator or denominator. So this gives us x squared sine squared of x over 3x squared. And then we have x squared over x squared. So that cancels. And this gives us the limit as x approaches 0 of sine squared of x over 3. And now I have absolutely no issue plugging in 0. Sine of 0 is 0. Okay. So all 3 of these paths led me to a limit of 0. So it's likely the limit equals 0. But that is not the end of the problem. I can't say that. This was only 3 paths. Again, I cannot test every single path. So we need to do more work to prove this. Okay. So this is where I'm going to utilize the squeeze theorem, because there's definitely no way I can algebraically manipulate this expression, especially because it's dealing with trig. Okay. So if I look at the expression on the inside, it's x squared sine squared of y over x squared plus 2y squared. If you think about this, every single term is squared. Okay? Because of that, I can immediately state that this is greater than or equal to 0. So that gives me a lower bound. Okay? And 0 is exactly what I want my limit to equal. So great, I've got one part of the squeeze theorem. Now what I want to do is I want to find an upper bound that also has a limit of 0. Okay? So what I need to do, because I've got a fraction, is I kind of want to manipulate this a little bit. So notice we've got this. And then also we have the following. So one thing we can actually do is if I make my denominator smaller, I get a larger expression. Because if you think of 1/2 and 1/3, 1/2 is more than a third. Okay? So the smaller the value in the denominator, the bigger your expression. Because you also have this relationship. 1 is bigger than a half, which is bigger than a third, which is bigger than a fourth. Okay? So if I can make my denominator smaller, then I'll have a bigger fraction. Well, in this case, y squared is a positive quantity. So if I get rid of this piece in the bottom, it gives me a bigger fraction. So this is at most then x squared sine squared of y over x squared plus 0. So I've taken a little piece off because the denominator, making the denominator smaller, creates a larger expression. So again, y squared was a non-negative quantity. If I get rid of it, immediately it makes my denominator smaller. So overall, my fraction is bigger. And the reason this is nice is because now the x squares cancel, and I have a nicer upper bound of sine squared of y. Okay? So ultimately, my expression that I'm taking the limit of is trapped between 0 and then sine squared of y. Okay? So ultimately, what we get then is our expression is trapped between 0 and sine squared of y. And now if I take the limit of each piece separately, the limit of this is 0, the limit of this is 0. Squeeze theorem, the thing in the middle also has to go to 0. So stating that all out, since the limit as xy approaches 0, 0 of 0 is the same as the limit as xy goes to the origin of sine squared of y, these are both 0 by the squeeze theorem. Again, got to state that result I'm using. The limit we were searching for is indeed equal to 0. So this limit does exist, and it is actually equal. What I am going to show you is you can actually get this a different way in case you didn't like that approach by making the denominator smaller. So really down here, another way. Okay. If you consider x squared plus 2y squared, the smallest that's going to be, or you can say it's definitely bigger than x squared. So now if I take both sides and divide by x squared plus 2y squared, this gives you x squared over x squared plus 2y squared is less than or equal to 1. Okay. And then from here, you know the right-hand side is also non-negative, so we get this inequality. And then you can go ahead and take this and multiply by sine squared of y because it's non-negative. It's not going to flip the inequality. And you end up with exactly the same thing. And then limit of this is 0, limit of this is 0, so limit of the thing in the middle is also equal to 0. So same way to get the bound, just different approach. Completely up to you what way you want to go about it, what you might see first. Okay. So to kind of summarize how you go about limits, especially when it doesn't tell you whether the limit exists or not, try a couple paths. If they all give you the same thing, that's the indication the limit exists, and you probably have to use the squeeze theorem. If you get two different values, you're done. Two path tells you it's over. The limit does not exist. And then if it's just a funky expression that has a square root, you're probably going to do a conjugate. These are really kind of the only three types of things that we can ask, purely because these are already complicated enough. So anything further would be very difficult, other than being able to directly substitute it in. Okay? So do your best with these, but just in the same sense that, limits didn't necessarily come back. You're not going to be calculating limits to go through our vector calculus. We're just going to take limits to introduce like the integrals and things of that nature. Okay. So the last thing that I want to talk about in this section is continuity, because we know the two go hand in hand. When we were dealing with continuity in Calc 1, you needed the limit as you approach that value to actually equal the output, and that's what gave you continuity. Really, exact same thing here. So we say a function f of xy is said to be continuous at a point AB if and only if three things happen. The first is the function is actually defined at that point. 2, the limit as you approach that point exists. And the third really just summarizes these two have to be equal to each other. If you just state the third, it's implying that the other two exist. So the limit is actually equal to the output of the function. Okay. So when you're talking about continuity of a multivariable function, it's continuous at its domain as long as it's continuous for every single point inside that domain. So the same issues you had before when you were taking natural log of x, it was continuous for x being greater than 0. You have the square root of x, it was continuous for x being greater than or equal to the square root of 0. So same exact idea here. You given that multivariable function, you find the problematic points, it's going to be continuous everywhere else except for those problematic values. So ultimately, we say f is continuous on its domain D if f is continuous at every point in D. Okay. So we'll do two examples. We're going to figure out where the following function is continuous. First one we're going to start with is, we'll call this one G. It is the natural log of x squared plus y squared minus 4. Okay. So if you think about the domain of this thing, it is all x and y values. As long as the thing inside is greater than 0, that's the same thing as saying x squared plus y squared is greater than 4. As long as x and y satisfy this inequality, you've got that function making sense. And then this function is going to be continuous for all x and y values that satisfy this, because you'll have no issues just directly plugging in that point, because you'll get a true output. And we know the natural log function is continuous. So ultimately here, G is continuous on its domain. And to give you a visual as to what that looks like, it's x squared plus y squared is greater than 4. So a circle of radius 4 is kind of your boundary cutoff. I can't equal points on the circle. That's a terrible looking circle. Let's scratch this. Let's try it again. I should use just the dotting tool, but that's fine. Okay. So here is our circle of radius 4. Cannot equal points on that boundary. So this is x squared plus y squared equals 4, because that will give us a natural log of 0. Because this is saying I can take all x squared plus y squared that's greater than 4. That would be anything outside. So this is the domain D. Okay. All right, moving on to our second and last example. We've got h of xy equaling arctangent of x over y. So if you think about arctangent of x, this is my absolute favorite function. The input for that is all real numbers, and it's tracked between negative pi over 2 and pi over 2. So the domain of this function is I can plug in whatever I want, but because I have x over y here, my arctangent function will be continuous as long as this inside function is also continuous. So ultimately, since arctan is continuous for all real numbers, this multivariable function is continuous everywhere this inside function is continuous. So the only time we're going to have issues is when this denominator equals 0. So the only problem occurs when y is equal to 0. So ultimately, your domain is I can take any x, y value I want as long as y does not equal 0. So if you think about that restriction, y equaling 0 is the x-axis. So if I were to graph this domain, this could be a solid line, but my x-axis would have to be a dotted line. And the domain is everything except that. So really, you kind of get to shade everything except the x-axis. So it really ends up just being the entire thing shaded, which is that dotted line to indicate it. So this is the domain. And then that arctangent function is continuous for everything else then. So this function h of xy is continuous on its domain. Okay. So exact same idea as with composite functions. Basically, just think of the underlying base functions you have. What are those issues?